Hello, class. Today we are going to look at the graphs of a logarithm, and I just want to call your attention to this page in our textbook. This has many of the different things that I'm going to go through already spelled out for us in here. So this goes horizontally C units left and D units up, and so I'll show you what all that means here in just a second. But what I want to do first is go back and remind you, in the last video I made, I showed you this is the way that a logarithm is defined in terms of an exponential. And I had said that a logarithm is nothing more than just asking a question about an exponent for what it would need to be for a certain thing to be true. And then we covered these two properties. And at that time, this is still the notebook I used, I called them the inverse function properties. And I said they were the inverse function properties because if you had an exponential function and you took the line y equal x and you reflected it across, this graph that reflects is exactly the graph that we get for a logarithm. And so these are, in fact, the inverse function properties. And just to take it one step further, I'll show you a little bit more, and that's this right here. If we let f of x be b to the x and g of x be log base b of x, then recall, so now I'm going to say recall here, that if this is true, if f of g of x equals x, and it's very important that there's an and there, and g of f of x is equal to x, then, and only then, f and g are inverses. So those are inverses to each other if those two facts are true, but both have to be true both ways. And so look at this. If I say what is f of g of x, f of g of x is f of g of x, and g of x I know is log base b of x. And now to do f of that log, whatever I put into f, that x, it goes up to the power as an exponent for b. So instead of an x there, I now have log base b of x, and so that needs to go up in the power. So this should be b to the log base b of x. And that, my friends, is exactly that first one right there. That equals x. And so in this game over here, we've done half of what we needed to show. I'm going to erase this now, and we're going to check it the other way. So now what I want to do is, what is g of f of x? Well, that is g of f of x, and that's g of, what is f of x? F of x is b to the x. And now what does g do to something? Well, whatever you stick in g, if I put in x right there for g, then what I do is I take log base b of that x. But I don't have x anymore. I have log base b of x. And so I should put a b to the x in there. And I know I said log before, I didn't mean to. So g then does log base b of what? In our case, it's b to the x. And that, my friends, is exactly property 2 I listed last week. That is also x, which then takes care of step 2 in the inverse function theorem. And therefore, we can conclude that an exponential function, being b to the x, and a logarithmic function, being log base b to the x, are truly, in fact, inverses to each other. That's really a very special property. Because, and I'm going to direct your attention over here now, I had said last time when we learned about the graph of exponential functions, we knew that the range was 0 to infinity. And a very nice property of inverse functions are whatever the range of one function is, that becomes the domain of its inverse. And so for that to be the domain, that's why, notice if that's the x and y axis right there, my logarithm graph looks like this, and it never is defined for any negative values of x or 0. And that is shown by the fact that I'm using a parentheses and not a bracket. And so then the domain for an exponential function, you could put in any number, because b to a negative 50 is the same as 1 over b to the 50th. And so that will still be a number, and it will still work in this function. So you can stick any number you want into an exponential function, so that domain becomes the range of its inverse. And if you notice, this continues to go up forever, and in this direction it goes down forever, and so it matches that the range should be all real numbers. Okay, so I just wanted to start with that, point this slide out, because this lecture and this section has everything to do with the graph of a logarithm. Taking that into account, then, let's go back and let's investigate this a little bit further. So I'm now going to switch over to Desmos, and here's what we have in there. So I am going to take a miscellaneous log base. I'm going to say b of x. And I'll add a slider for b. And I'm going to make b 0 and 1 and step by 0.1. All right, so there is the graph of b to the x if b is between 0 and 1. And so notice it is the opposite of the graph that I have in the notes. So in the notes, we're looking at a graph that looks like this. I will tell you in a second why that is true, but I just want to point it out for now and show you that I'm not hiding anything. Now then, I'm going to change this from 1 to, let's say, 20, and do the same thing. And now if you look, all that happens as I change that b is it just bends that curve a little bit more. And so it just bends it. It doesn't do anything in the end. They're all still going to raise higher and higher and higher. And you do have to go out a long ways to see that it continues to grow. But if I can get a point on here, there you can see that as my x goes up, I'm at 3.611, 12, 14, 15, and so it does keep growing forever. It just grows very, very slowly. But that has everything to do with the fact that if I graph b to the x, as I change it, you see they bend in equal and opposite directions across that very line right there. This shows in real time with a variable as the base for the logarithm that it in all cases is a reflection of an exponential function. So it shows that they truly are inverses to each other. Okay, so then let's now go to the homework problems. Oh, now let me show you what all of these pieces mean in here. So I've shown you the logarithm itself, and now let's investigate what different pieces do to it. So let's bring up and have a logarithm again. I'm just going to leave it at 3 because you know as that 3 changes to other things, and here I'm even going to just make it a 2 right now. What I'm going to put in there, though, is x minus c. And we'll add a slider for c, and I'm going to make c be strictly positive. Okay. And so, one thing I want you to see is if I let x equal c, right now c is 0, so x is 0, and it is the x-axis. As I grow the value of c, when it's 2, notice the vertical line now, green, is at x equals 2, and that's evidenced by that function 3 right there. The log of x minus 2, now if c is 2, it'll be log of x minus 2. And since it's a minus inside, same thing with parabolas and quadratic functions, that minus is going to drive the function to the right. And so as I move it, notice I'm moving that vertical asymptote there. That's going to play a role here in just a second. I'm going to tell you something about it. But as c grows more and more, that graph slides further and further to the right. And so, coming back to this, notice it says it is horizontally c units to the left. Now, why is it c units to the left? Because that's a plus in there, and I used a minus. And so if a plus makes it go left, a minus should make it go right. I'm going to change it now, and all I'm going to do is make that a plus. And then this time, I'm going to make that a minus. And as we had before, there it is if c is 0. It's not shifted to the left or to the right. It really is the inverse of whatever 2 to the x looks like. But as c grows now, since c is positive in this case, and now it's like c is a positive 3, so now we have log of x plus 3. That plus is going to drive the function to the left, and therefore you can see I needed to use a negative c in for that vertical asymptote there to offset the fact that the plus is actually driving the function to the left. And so back to this, that's where the horizontally c units to the left come from in the book. Let's now investigate this d units up and down. So the next thing I want to draw your attention to is, let's take log base 2 of just x, and now I'm going to go plus. I'm going to keep it like the book has. I'm going to put a d there, and I'm going to make d be positive, so we'll go 0 to 10. And we will change by 0.1. Okay, so notice if d is 0, we haven't shifted it up or down at all. And that you can see by the fact that the red and the purple graph lay on top of each other. Now, as d grows and gets larger and larger, you see the graph starts to move up. And if I turn this graph on, there's the original graph. So now we can see there they are together when d is 0. And as d grows, that purple graph starts to deviate by shifting up. If we go back to the book now, notice in here it says it's vertically d units up. Well, if a plus d makes it go up, a minus d is going to make it go down. And so if I did nothing but change that to a minus, now you can see it goes down by that much. So we start out even with the original function, the parent function, and as d grows, now we're subtracting a positive number, and that's going to drive the function downward. And so you can see the movement happen right there as I allow d to grow. Okay. In here, in a out front, they say it stretches it, and so let me show you what that looks like in here. So I'm gonna leave it as log base 2, but now what I'm gonna put is an a times out front, and in this case, if a is 1, they should be the same. And so now what I have is a multiplier out front, and a multiplier, remember, is a vertical stretch. And so what this should do is take these graphs as they lay on top of each other right now and stretch the purple one in the vertical direction. So watch that come into fruition as I let A get larger and larger. It's not that it's shifting the whole graph up. You can see it stays at that point right here at 1 comma 0. And so, but what is happening on a larger scale is I'm stretching the other graph up further and further as I allow A to grow larger and larger. So that is that vertical stretch. In that case, it is a compression if A is less than 1, meaning it's a fraction out front, it'll compress it in the y direction. If you throw a negative out front, it flips a graph upside down. You know this is the graph of x squared, and if you put a negative out front, it turns the parabola upside down. If you throw a negative inside, it's a reflection across the y-axis. I'm going to show you that right now. The easiest one to see that with would be if I graph square root x and square root of negative x. There you can see that the green graph and the blue graph are flips right across the y-axis. I had to use a function like that because if I did x squared and negative x squared, you would say, well, they look exactly the same, so it doesn't look like anything happened. And in reality, something did happen. The parabola did flip, and the left side went to the right side, and the right side went to the left side. It's just that since it was symmetric already to begin with about the y-axis, you can't tell the difference. So, putting a negative in does flip it across the y-axis, and so that would be there. And general, it looks like that. So then they just summarize it one more time in this, but we're going to use that as our basis to answer the questions. In order to do that, I'm going to add a couple pieces of notes to this. So here's what we've learned. The graph of a logarithm looks like this. It always goes through the point 1, 0 if this is just log base b of x. The domain for it is 0 to infinity, and the range is negative infinity to infinity. It does have a vertical asymptote at x equals 0, and we could put that right here and dot it in along that y-axis. The y-axis is the equation x equals 0. So that's the information that we have. Now look how I used that knowledge to go about answering the questions in the book. So in this first set of problems, the directions say for the following exercises, state the domain and range of the function. Okay, first things first. This makes it go left 4 units. This does something else. We'll talk about it in a second. This, it stretches it, it shifts it, and it moves it down 2. This, it does the same thing, moves it down 5. This, kind of the same thing, and it moves it down 3. The thing is, with all of these, when you have a graph that's shaped like this, and you move it up more, or you start here and move it down more, if it's still going to go all the way up to positive infinity and all the way down to negative infinity, the range will never be anything else for these problems. So the range was all real numbers, meaning that goes down forever and that grows forever, and I showed that in Desmos. And so we do hit all values. So however you shift it left or right, down or up, it's still going to go all the way to negative infinity and all the way to positive infinity. So the range for all of these problems, the range is negative infinity to infinity. You cannot change the range of a log function. What will change is the domain. And so here is the next thing. Notice the domain is that only from 0 to infinity. Another way of saying the interval 0 to infinity is x strictly greater than 0. So we want x strictly greater than 0. Notice, and here's the truth, The x in here is called the argument of that function. And so you need the argument to be positive. Another way of saying this is you can't take the log of a negative number. I'm going to show you that right now. Watch what happens. In this calculator, if I cleared everything and I said, what is log of negative 3? It's going to tell me it's not a number. And so it knows that you can't log negative values. In this, if I said, what is log base 3 of negative 6? It won't even let me do it because it knows that that's not possible. If I took any other value that was positive, it would execute it and tell me what the value is. So the fact that if I put a negative in there, it's asking me plus what? If I put a 12 there, it'll now tell me the answer to it. So I can't log a negative number, and that is because the domain is only positive values. So the argument must be positive. What that means is any one of these problems, the way to set it up is in problem 6, I need x plus 4 to be greater than 0. So if I subtract 4 from both sides, I need x to be greater than negative 4. Well, greater than negative 4 on a number line means there's negative 4. Put an open circle. And since x needs to be greater than negative 4, we're going to shade to the right. And so notice I'm shading to the right. And so as an interval then, that would be negative 4 to infinity. I'm going to show you something cool here. So negative 4 to infinity is the domain of this function. So I'm going to say the domain, negative 4 to infinity. Then the range we already discussed. That's negative infinity to infinity. Now, let's talk about another way to think about this. We have just seen that that plus 4 should drive the function left 4. Well, if normally the function has a vertical asymptote at 0, notice that's why I included it here as dotted in red in that case. It was to set you up for this. So normally, this is the graph of log 3 of just x, and it does have an asymptote at 0. But the plus 4 is going to make it go to the left 4. So that means now I've got an asymptote at negative 4, and it goes like that. If that's the case, and you have this at negative 4, then the domain is negative 4 all the way to infinity. And that's exactly what we said right there. So instead of thinking about it in terms of algebra and this inequality that we needed to solve, we could think about in transformations of functions, what does replacing x with x plus 4 actually do? And in doing that, it drives the function to the left by 4. So then if the original domain was 0 to infinity and you went left 4, now it should be negative 4 to infinity. So there it is right there. I'm going to graph that now for us so that we can see exactly what it looks like. And here is that graph. So we have log, it was base 2 of x plus 4. And I'm going to show you now, if I give us x equals negative 4, there is a vertical line at negative 4. You can see that the function does touch, or it is asymptotic there. And as we go down, it gets closer and closer and closer. But it never will touch. And if we ever get into a bind, we can just zoom in more, go down further, and it will slowly forever go to infinity and forever get closer to that green line. But that shows us that from negative 4 all the way to infinity, we have red dots. And so because of that, that is where that function's defined. So that is where the domain actually is. Notice it still goes all the way down to negative infinity out the bottom, and out this side, out the right-hand side, it does continue to grow forever and ever and ever. So out the right, it will end up at positive infinity, and out the bottom, it will go to negative infinity fairly quickly. So the way that you think about all of these problems is you would set 1/2 minus x greater than 0. In this, you would set 2x plus 9 greater than 0. In this, 4x plus 17 greater than 0. You get the point. So the point is, whatever the argument is in there, it has to be a positive number. You can't take a log of any negative value, including an ln, because ln is nothing more than log base e. Down here it says state the domain and the vertical asymptote. Well, this, it went left 5, or it goes right 5, so the minus is going to drive it to the right 5. So that means now we have an asymptote at 5, and it looks like that. So what is the domain in 11? The domain is 5 to infinity. And what's the vertical asymptote? Would be at x equals 5, because that made it go right 5. If you look on the graph, we have log b of x minus 5. So let's keep it accurate. Let's say log b of x minus 5. Add a slider for b. And if I say x equals 5, so the vertical line in red is at x equals 5. You can see that is a vertical asymptote to the function. And whatever I change b to, all it's going to do is just change how the function bends. And as long as b stays positive, it always stays asymptotic to x equals 5. It's always defined for greater than 5. And we figured that out when we looked here. We said we want x minus 5 greater than 0. If we add 5 to both sides, we would want x greater than 5. X greater than 5 means at 5, we would put a dot and shade to the right. So that would be 5 to infinity. And notice that's exactly what happens when you drive the graph to the right 5. You do go from 5 to infinity. So the answer to this problem is the domain is 5 to infinity. The vertical asymptote is x equals 5. In this one, you would set 3 minus x greater than 0. You can figure out, well, I'm going to show you this one because this is a kind of a special one. So watch what happens with that. I'm going to even take it over into the notebook. So I'm going to do this. No, I can't. So I'll just take it over. ln of 3 minus x. So watch this now. So what we have is y equals ln of 3 minus x. Now notice, all the problem's asking for is what's the domain and what's the vertical asymptote. But I like to think in terms of the graph. And so here's the way that I think about it. I don't know really what happens in this. I'm going to show you what happens at the end, because I'm pretending right now. There's a real cool way to show exactly the behavior and how this happens, just in terms of transformations. But I'm going to show it to us first from an algebraic standpoint. To get the domain, what I need is 3 minus x to be greater than 0. In this case, I'm going to add x to both sides. And now I need 3 to be greater than x. Well, 3 being greater than x is the same as x being smaller than 3. I tend to like to use this one more, because then I can see if this is 3 and I need to be less than 3, then it's everything this way. So that means I need to be at negative infinity up to 3, but don't include 3. Since that's the case, then I can see that must be true that x equals 3 is my vertical asymptote. So all I've used in this class is nothing but an algebraic inequality from the fact that I cannot take a log of a negative number. And so another way of saying not negative is that it has to be positive. And so positive means greater than 0. So in that case, but now watch this. So now we're going to look at the graph. So ln of 3 minus x. So watch this. Before we do anything, I'm going to put x equals 3 in there. And then we're going to say ln of 3 minus x. Notice on this graph, it is defined all the way up to 3, but it's not defined after 3. All the way on the positive side over here, there's never any green dots. But over to the left, all the way down to negative infinity, we can have values all the way down there. And so here's how we could have figured that out a different way than just using this algebraic approach. If I took 3 minus x and pulled a negative out, I would get negative 3 plus x. And if I rewrote that, it would be negative x minus 3. So ln of 3 minus x is really the same as ln of negative x minus 3. Okay, what does that negative do in front of the x? It flips it across the y-axis. That, my friends, you can get from the book right here. If you have a negative in there, it reflects it about the y-axis. And I showed you that a root function goes like that, or it flips like that. A log function normally goes like that. It'll flip, and it will look like that. And so a negative in front of the x flips it across the x-axis. And then what does the minus 3 do? Well, the minus 3 makes it go right 3. So if I then drew a graph and said, okay, it has to move right 3, so the normal spot that sits there at 0 now gets moved over to 3. And then normally my graph would then look like this, but because it's flipped, it now needs to look like that. And so I'm going to draw it like that. And if we go back, that is exactly what it looks like. So this picture right here and that picture are nearly the same. And so you could get it through transformations by working with the argument in there and manipulating it to see, oh, that's a negative on the x, so that's going to flip it. Oh, and then the minus 3 makes it go to the right 3. And so then if it goes right 3, but then gets flipped, this is the correct graph. And therefore you can see why Desmos graphs it the way that it does. So understanding that in this is, I think, a kind of a neater way of doing it. This is safe because it'll always work. If you always just put greater than 0 there, it will always tell you what's happening. Notice earlier in the book when we approached these problems, I said, well, this one's a little different, but we'll talk about it. Because that minus is on the x, instead of going that way, it flips and goes that way. So the domain's going to be different. But if you set it greater than 0, it will still work for you. But if you've pulled out a negative and made it negative 1/2 plus x, you could see that it's negative x minus 1/2 And so it's moved right a half, and it's flipped that way. So then the domain, you could say, is negative infinity to 1/2, and the range would still be negative infinity to infinity. Here, state the domain, vertical asymptotes, and end behavior. The end behavior is just, does it go to infinity to the right, as x goes to infinity, y goes to infinity. That's the kind of information they want in there. In this one, state the domain and range, x and y intercepts, if they exist. The x and y intercepts, I will do another video tomorrow and upload it to show you how to get those, because those are a bit different. But we will look at the exponential function first, and then we will change from there. The final thing that I'm going to show you on here before I cut this off is in this graphical section down here. Notice you have a log, which it's implied the base is 10. An ln, it's implied the base is e. E is approximately 2.717828. Then you have a 2, a 5, and a 25. So what is happening in this is the b is changing. So b goes from 10 to 2.7 to 2 to 5 and 25. And so what we want to know is what happens as b gets bigger and bigger. Well, let's go over here and let's investigate. So if I take log base b of x, and I put a slider in, and we change from 1 to 20 and go by 0.1. So here is what we have. As the number gets bigger in the base, so the base is now 2.3, now the base is 3.2. Notice the function gets sharper, meaning that it grows slower, seemingly, as x gets more positive. And so the higher numbers would correspond to a lower graph out on the right-hand side. What I mean by that is the following. So remember, in this, we had 10 as the base, we had 2.717 as the base, 2 is the base, 5 is the base, and 25. So the smallest one, 2, should be A. So that one should be A. The next smallest one, 2.7, should be B. So that should be B. Then we have the 5. That should be C. Then D should be the 10. And E should be the 25. So I got that idea from looking at the base in that and saying, oh, they're just changing the base. We went to Desmos and said, well, what happens when you change the base? And when you change the base, it changes the bend and makes the bend sharper, I call it. And so in here, as that base grows or changes, it should change and get sharper and sharper. And so that's the way to think about this. I hope that helps. The other graphs, it's more just look at Desmos, investigate what happens with fractions. In these, these just verifies that they're inverses to each other. That's what they want you to see, is that kind of stuff works for that. In this case, it's more just what does the negative do, how does it shift it around, and all of that. So all of these functions, it all comes back to you want that to be greater than 0, and then you want to see where does the asymptote lie, is it flipped or not, and then you sketch it. All right? So hopefully that helps. That's enough to get you started anyway. I will upload this and get you started. All right? Hang in there, guys. Take care.